I grew up about 12 miles down the road from here in Whitwick. Anybody placement at Whitwick, Colville, that neck of the woods? How's it going? Good. That's relief, right? That's very nice to hear. I'm now training the next generation of outstanding teachers at the University of Roehampton, a rule not that different from what Doug does. They let me out occasionally to do other things, as Doug says, writing some of the National Curriculum Programmes of Study for Computing. Blame me or thank me, depending on your perspective for that. But the Leicester Association goes further. So I remember at the age of 10, it would have been, coming to a brilliant open day at Leicester University. And that got me interested in higher education and going on to do well in A-levels and becoming a student. And then I came back to Leicester and did my master's here, although admittedly by distance learning. So I think this was taken about 8 years ago, almost to the day, not quite the 8th anniversary of my master's graduation. So happy memories. Right, on to the new computing programme of study. Our first sentence sets out our ambition for what we're trying to do with the programme of study. A high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. Firstly, nothing there about coding. Despite what you might have heard from the media and despite what you might have seen happening in some schools, this is much more important than typing instructions into a computer. This is about understanding the world. This is about changing the world. Secondly, Ofsted coming to check whether it's working or not, easy for them. They just go up to a child, ask them 2 very simple questions. Have you understood the world? Have you changed the world? Tick in both boxes, job done. Yeah, we've sorted once we get to that. I think it's a pairwise thing. The computational thinking is about understanding the world, and the creativity is about changing the world. Getting children to the point where they've made something on a computer that has never been made before is what we've been doing in ICT education for a long time now, and is a great thing. It really is. So please don't lose track of that creativity side of the curriculum. You do want children working creatively with the digital tools that they have at their disposal. But the computational thinking thing is perhaps relatively new. And admittedly, as a term, this has only been in existence sort of about 10 years or so. So I think we need to think a little about what we mean by computational thinking. If I had a little longer, we'd do the whole, okay, what do you think it means? And then I'd show you the answer on the card. Let me tell you 2 things which it isn't. It isn't thinking like a computer. They're dumb machines. They don't yet think, okay? They just follow the instructions that they're given. And please don't say you want children in school to just be following the instructions that they're given. Well, perhaps once in a while, children following the instructions they're given may not be a bad thing. But computational thinking isn't simply about following instructions. It really isn't. Also, I don't think you can say it means thinking like a computer scientist, at least not when you're talking about primary school children. Being a computer scientist takes years of training and experience and practice with programming and so on, and you can't seriously expect a 9-year-old to be able to think like a computer scientist. Perhaps, though, on a good day, you can expect them to draw on some of the concepts, some of the approaches, some of the techniques that computer scientists, software engineers, programmers routinely use in their line of work. So what is computational thinking? In the Quick Start Primary Handbook, I start by saying, well, generally, when we get computers to help us with things, it's a 2-step process. Firstly, you've got to understand the thing that you're wanting to do. Even if it's word processing, even if it's making a presentation, your first stage is not to go and type at the keyboard or move things around on screen. Your first stage is to understand the problem, understand the system. Think about the steps, think about the rules, think about the problem, think about the system. That's really hard, creative, original thinking work. Your next stage is to get the computer to help you with that, to actually put your fingers on the keyboard and start typing the thing, or to move things around on screen, or to write some code. And I reckon computational thinking is the first part of that process. It's about thinking about systems, thinking about problems in such a way that a computer can help us understand those or solve those. Now, yes, this certainly does apply to the process of writing programs, But it's more general than that. As I say, if you're typing something up, word processing something, you've got to think about audience, you've got to think about purpose, you've got to think about structure before you start your typing. If you're making digital video work, you've got to think about storyboard and script and synopsis and so on before you get involved in actually pressing the red button and recording the video there. And it's that first stage that I think we really ought to be concentrating on in a lot of what we do in computing. Who's seen the Barefoot computing resources? Okay, so that's a marketing budget which we possibly ought to have devoted more money to. Never mind. Okay, so for Barefoot computing, what we've tried to do with Barefoot, this is BCS and British Telecom scheme, to give primary school teachers just enough computer science subject knowledge to be able to teach the national curriculum in their school. So it's enough to get you going, is the idea there. And we've taken computational thinking as a significant theme in developing these Barefoot resources. So what we've done, taking a lead from Julia Briggs' work at Somerset County Council, is to split computational thinking into two parts. Over on the left there, the concepts, the ideas, the processes, if you will, the logic, algorithms, decomposition, patterns, abstraction, and evaluation that computer scientists, software engineers, programmers use routinely in their line of work to understand problems, to be able to understand systems. And then a cluster of approaches which they also seem to favour, but they're somewhat softer about tinkering, about making things, about debugging things, fixing things when they don't work, about persevering when it gets hard, and about working together, although the exam boards tend to discourage that bit. What I'm going to do is go through those in a little bit more detail now. Have in the back of your mind not just, yes, I can see how that relates to computing, but also think about how it relates to other bits of the curriculum and how it relates to your emerging craft as a teacher, because I think they do apply in other domains too. So firstly, let's start at the top with logical reasoning there. Computers are deterministic machines. You set them up the same way. You give them the same input, you run the same software on the same hardware, they will produce the same output. They're predictable. We know what's going to happen if we set them up in a particular way, unless, of course, you're running Windows 8, in which case other circumstances pertain. Don't you want children to be able to give the reason why, to be able to reason logically about things? Isn't that something which we ought to be teaching in primary school? Shouldn't they be able to spot the flaw in a logical argument? Here's a logical argument for you. Some children learn really well through learning systematic synthetic phonics. We want all children to read, therefore all children should be taught systematic synthetic phonics. Anybody spotted a logical argument in that, logical flaw in that argument? We won't go into that detail. But that being able to make deductions from premises is a big part of logical reasoning. You then have the scary A word. When we went out for consultation, we had a number of the sort of advisor and consultant types coming back and saying, you can't possibly use words like algorithm with primary school teachers. Look, it's got at least 5 syllables in. My response was, this is a generation of teachers who are using phrases like split vowel digraph with children in reception. What's wrong with the word algorithm here? When we're talking about algorithms, we're talking about sequences of steps, sets of rules in order to get something done. You were doing that for the last 4 weeks out on placement. Did you not have a sequence of steps that children had to follow to get ready for lunch, or to get ready for work in the morning, or to pack the classroom away at the end of the day? That's an algorithm to get something done. Over in English, we might once have called it instructional writing. Over in science, we call it the method for our experiment. Over in design and technology, you often call it the recipe for something. Sorry, is that me? No. Okay. Over in computing and in maths, we call it an algorithm. It's a sequence of steps, set of rules to get things done. Okay. Computer science is looking at a problem or looking at a system. We'll look at the parts that it's made up from. So look at the big... Oh, I remember the Director of Studies of my former school. What was the thing? Brilliant assembly on how do you eat an elephant. Anybody in the room? How do you eat an elephant? One bite at a time, yeah? If you've got a big problem, complicated system, don't try and tackle it all together. Break it down into smaller parts and deal with each of those parts. And that's exactly how we write software, how big software engineering projects get done. Okay, the secret here. A good computer scientist is a lazy computer scientist. This does not mean, by the way, that all lazy computer scientists are automatically good computer scientists, but a good computer scientist is always looking for an easier way to get things done, looking for the way that other people have solved similar problems, drawing on that experience, seeing where the common patterns are to solving big classes of problems. Better to solve lots and lots of problems through using a general pattern than to have to solve each of them in turn. You teach children a general rule for multiplying two-digit numbers. You don't make them learn their times tables up to 100 times 100. Yet, wait for the new edition of the maths curriculum, perhaps. So, looking for those patterns, being able to generalize the rule. Good, important part of computational thinking. This is the key to the whole thing. For Jeanette Wing, who coined the term computational thinking, she says abstraction is at the heart of computational thinking. And abstraction is about managing complexity. That if you have something which is difficult, which is complicated, the idea of abstraction is we take that and some of the complexity there and put it to one side, put it inside a black box, say that we can worry about that later or that we have other people to worry about that level of detail. In many ways, the journey from ICT to computing is about going inside those black boxes, or inside at least the first layer of the black boxes. We cross what we call the abstraction boundary. Back in the days of ICT, how does Google work? Well, you type it in and click the button, was pretty much what we would teach children. Okay, there are refinements to that. Now, in terms of computing, we're interested in the process there of how Google select and rank those results. Other search engines, apparently, are available. Yeah? So that level of detail becomes something we're concerned about. But we're still not concerned about how Google actually manage their data centers, where that data gets stored on magnetic hard drives, how that's replicated across multiple servers. That level of detail we still leave inside the black box and worry about that later. So writing code is very often a case of dealing with that abstraction. Capture the important detail, leave to one side the less important stuff. So that's in terms of those processes, the concepts of computational thinking. I want to talk a little, though, about how computer scientists, software engineers, actually go about their work, because I think we can draw on that too. And I'd start in terms of these approaches by talking about tinkering. A willingness to play, a willingness to experiment. Those of you who've been fortunate enough to be working in early years or Key Stage 1 will have seen children just picking up technology or picking up things and playing and exploring and experimenting and tinkering with those things. And that surely is how they learn how the technology works. My 4-year-old daughter, her first creative work, I'm almost ashamed to say, was done on the iPad. She'd watched Mummy and Daddy using the iPad, sat there at the age of about 4 months and started stroking the screen, drawing on the screen, swap into Brushes app, and there, that's her first finger painting. She'll never remember a time when she didn't know how to use an iPad. That's really worrying in some ways, bad parenting stories, I know, but what you have there is her willingness to play, to experiment, to tinker with this technology. And very often, if you look at how software developers, computer scientists approach their work, they'll start by play, experiment. There's a playfulness to that. Further up the key stages, we have to talk about experiment and exploration, or indeed tinkering. Photo, by the way, or picture, by the way, 19th century German kindergarten. Would it pass its EYFS inspection? I don't know, but they've provided a wonderfully rich learning environment there. Okay. Computing is at its heart a creative subject. The best way to learn this is to make something, yeah? I really do worry about some of the computing materials I see where it is do this instruction, do that instruction, do that instruction. One of my trainees returning from placement talking about the child in her class who was told off for colouring in the sprite the wrong colour. Yeah? It's meant to be creative. You're meant to be making something that wasn't there before. Seymour Pappert's work with Logo, back in the very, very early days, children learn best. They make these mental schema best through the act of making something to show to others which embodies their understanding. And of course it will go wrong. Isn't that the fun of computing? Isn't that the fun of coding when it doesn't work as you expect? When your mental model of how the computer works, your logical reasoning, it should do this, actually there's a conflict there because it doesn't work as you expect it to. And those of you who've been reading Carol Dweck and growth mindsets will know how important it is, how children react when things do go wrong. In computing, they get that feedback immediately. Back in the old days of ICT, you had to go around and mark their presentations and say, yes, that's very lovely, but it would be much better without quite so much word art and quite so many different transitions in there. And I'm not sure about the clip art, and I'm not sure about the sound effects. Less is more with PowerPoint. These days in computing, the computer gives them that feedback for their code. Either it works or it doesn't work. Either it compiles or it doesn't compile. Either it's fit for purpose or it isn't fit for purpose. You have a really tight feedback loop, encouraging children to debug their own code. The new program study says they have to use logical reasoning to detect and correct errors in their algorithms and programs. Absolutely right. It doesn't say they should use their friend or they should use their teacher to detect and correct errors in their algorithms and programs. Your first response to, can you fix my program for me, miss, should be no. Fix it yourself. Use logical reasoning to do that. And of course it is hard. Hard is good. We know there's proper research behind this. Don't ask me to cite sources, I won't. That says that children learn more when they're working with difficult material. I've spent a little time with my niece over the weekend. Grew up around here. And she, when she was back at primary school, I said to her, is there anything you found difficult this term? No, Uncle Miles, it's all been easy. That primary school, to my mind, was doing a disservice to her. How will she cope? How does she cope when things start getting difficult? And that's one of the great things about programming, about computer science, that it is difficult, and you've got to stick at this to do well. Carol Dweck, growth mindsets, and all of that. And finally, in terms of approaches, don't forget, when you're teaching computing or computational thinking, that this is a collaborative process. Let them talk to one another. Let them work together. We have good evidence from the software industry that software is better, more reliable, and more fun to write when you have two programmers sharing a keyboard, sharing a mouse, working together on the same programming task. The picture here is one of Google's offices. Looks so much more like a kindergarten than the sort of call center which we set up in school computer labs. Go figure, hey. Okay, so in the national curriculum you have, I'll just pause for breath as much as anything else. Does anybody want to argue with any of that? Always up for a good argument. Okay, any comments, observations, questions? I'll show some more slides. Okay, over in the national curriculum there is this sense of progression to the computational thinking. This was not entirely deliberate in our minds, but it's how it worked out when you started drilling down into the detail. There's decomposition for you. Key stage 1, children should understand what algorithms are and use that logical reasoning stuff. I don't think it's a phrase mentioned anywhere else in the national curriculum. Oh, an aside, did anybody see the TES Leicester survey of how people are coping with the new computing curriculum last July? Miles, we were back at university in those days, we weren't worrying about the whole teaching thing, no. Okay, so the TES Leicester did a survey of, 1,500 teachers about how they felt about the new computing curriculum. One of this cluster of questions was, how much of this do you use in your daily work? So how much, they asked the question, how much logical reasoning do you use? And what we found in their survey was 14% of head teachers said they used logical reasoning. Does make you worry how the other 86% make their decisions, though, doesn't it? Okay, up into key stage 2, solve problems by decomposing them into smaller parts, and then use that logical reasoning to explain how the algorithms work, and as I said earlier, to detect and correct errors in algorithms and programs. So you have key stage 1, algorithms, logical reasoning. Key stage 2, we add in decomposition. Not really interested in key stage 3, but for key stage 3, we bring abstraction to the party there, design, use, and evaluate computational algorithms, and similar stuff around logical reasoning and algorithms, of course. Key stage 4, develop and apply their analytic problem-solving, design, and computational thinking skills. I could see that as some coverage for that pattern and generalization stuff if I really wanted to. So we start with algorithms and logical reasoning, add in decomposition, add in abstraction, and then bring in patterns and generalization. Just because it's left till later doesn't mean you can't start it sooner. I've already told you what an algorithm is, so this is a silly one to do as a group exercise. Sequence of steps, set of rules to get something done, okay? Unambiguous procedure, precise step-by-step guide to solve a problem or achieve a particular objective is what we put in the primary guidance. For me, programming, like the whole how you use a computer thing, is a two-step process. It's algorithms followed by code. How you solve the problem is the really interesting territory here. Thinking that through, thinking of the sequence of steps, the set of rules to get something done, is where so much of your and your pupils' creative thought is going to go. You then have the task of making the pooter do it, and that's where the coding stuff comes in, of translating those ideas of your algorithm into a particular set of symbols in a particular computational system, the language in which you write your code. Both of these are difficult, both of these are creative processes. Anybody with a degree in modern languages in the room? Okay. Did you ever, hello Lizzie Bo, did you ever have to do the translating poetry thing? No. You tried to forget about that. Okay. Translating poetry is hard, but so is writing poetry. The analogy is a flawed one, but think of the algorithm as the coming up with the idea for the poem. Think of the coding as the translating that into a particular target language. You have to know the grammar, the syntax, the vocabulary, all of those spelling, punctuation, and grammar rules apply in the translation process. It's still creative work, but it's a different sort of creativity from how you solve the problem in the first place. Can you have one without the other? Yes, you can. You can have children thinking of steps to get something done. We do that in cookery. What's your recipe for pizza here? That's almost a rhetorical question. We also can have children just doing code on its own. Here, I've thought of how to solve the problem. Now type in the instructions to make that happen. But if you split them apart like that, you lose a lot of the fun if you do the algorithms without the coding, and you lose a lot of the reason if you do the coding without the algorithms. The two really do work well, hand in hand, I would argue. So what is an algorithm? Sequence of steps, set of rules to get something done. Have a look at the flow chart on the board, which doesn't show up very well, but there you go. Okay, what you've got there, flow charts aren't the same as algorithms, it's just one way of representing an algorithm. This is where I stop talking and wait for somebody from the audience to respond. What does this algorithm do, please? Okay, they're talking amongst themselves, which is good. Go on, sir. Yeah, it's your mental arithmetic warm-up, it's your spelling test, it's something like that, isn't it? Have you all done the Skinner behaviorism stuff? Stimulus, response, reward, that's that, isn't it? Stimulus, I asked you a question, it's what we just did there. The pupil responds, and is the answer correct? Say yes, well done, or no, that's wrong, have another go at that. Yeah? Is there anybody in the room who's not used that algorithm in their line of work? Okay, there are other approaches to teaching, but this is pretty good for practicing your tables. It really is. Stimulus, response, reward. Okay. Here, on the other hand, is some code. Is there anybody in the room who's ever programmed in Python? Well done. Nobody else? Okay. Give you a moment or two to read the code on the board there. Treat it as if it was poetry in a foreign language if you wish. What does that Python program do? Talk to your friend or person who sat next to you and assume that they're your friend. And I'll take answers from the floor in a moment. there. A little bit more subtlety is when you spotted something else that wasn't covered in that really very, very comprehensive answer. I'm supposed to say round up. Okay. Anybody else? Spot anything else? Okay, I'm going to have to ask the question here. How many questions were to ask? 2 questions? 10 questions again. I am introducing PGCE. Okay. Before I arrange 10 there is say the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For each of those numbers, then go around this loop where we ask those questions now. So you don't have to teach children in primary school to program in Python like that. But in a random room of, I don't know, about 150 PGCE students, we found at least one person who figured out pretty much exactly what the program did. Did the rest of you have vague ideas? That was a shock when you were following that set. No? Because I don't want to do hands up if you haven't a clue what's going on, so we're doing that. But that's not a difficult thing to look at that code and figure out what's going on. In primary school, we use a much simpler programming language, and I hope everybody in the room has seen some Scratch before, because Scratch is pretty much our go-to language for programming in the primary phase. It doesn't show up brilliantly on the slide. Have a look at that. Can you tell me what that program does that's written in Scratch? I like Scratch. Anybody over this side figure out what it does? Who's figuring out what it does? Good. Okay, thank you. Okay, so we've got an answer here. Does exactly the same thing, yeah? Same program, same algorithm, but not the same program, strictly speaking. So we've still got we're going to ask 10 multiplication questions, 1 to 12. So we can all the essential introduction of 12 times 10, really important to do that. And shillings and pence coming back, you never know. Okay, so it goes through, ask the same question, ask 10 random questions from that 1 to 12. There's a subtle difference here. Did anybody spot one difference between them? Okay. Okay, it says think again rather than just dismissively no. There's another difference. Lizzie Mo?
It says it doesn't print it out, and it changes it up to the score by 1 as well.
Yeah, the score is the significant difference, which wasn't in my algorithm, because we all know how important it is to keep a record of what children have done in these tests. So Dan, are you in a school that's using education system mathematics, that sort of thing? Yeah, isn't that pretty much what education system mathematics does? Yeah, I'm going to answer these questions. If you get them right, I'll tell you, keep track of the score. So you can get children writing those programs. My point here is not so much the code, lovely as that is, but do you see the difference between the algorithm and how that gets implemented in one system or another system? Okay, how are we doing for time? Right, do you want your pupils to grow up to be architects, or do you want your pupils to grow up to be bricklayers? Do you want them to be the people who design the algorithms, or the people who have the job of coding those algorithms? And I present that in such a way that you're expected to give the answer, of course I want them to be architects, yeah? But no! Actually in computing, you kind of need to do both the architecture and the building work, yeah? Doing one without the other isn't what we're trying to do with the primary curriculum. Yes, our target is computational thinking, but our way to get there is through the craft of writing the code. Writing the code is the lab work for this, really. So why do we teach children programming? The practical experience of programming is almost certainly the best way for primary pupils to learn about computer science. Is there anybody in the room who during lectures does that really, really annoying thing of asking lecturers, where is the evidence for that? Okay, you need at least one person in each of your teaching groups to take on that role. Challenge us when we make these statements without any substantiation to them, okay? So he says here, the practical experience of programming is almost certainly the best way for primary pupils to learn about computer science. Was there anybody in the room who's thinking, is it? Prove it. Where is your evidence of that, okay? My evidence for that, well, clearly there's a citation at the bottom, Berry 2013. Got away with it? No, not quite, okay. There may well be. But I have no evidence to offer you in support of this statement.
moment. And we've got to fess up to that, okay? This is a new domain, well, almost a new domain. We're cutting fresh ground here. There aren't the papers written saying, we tried this approach where we taught the children computing through entirely unplugged approaches about making cakes, hello Lizzie, and making pizza and all of this sort of unplugged approach to computational thinking. And then we taught these children programming in Scratch. And at the end of the year, the Scratch group had scored so much higher on the test of computational thinking. I want that evidence. I reckon between 4 and 8 million, and we could get that evidence. Really, we could. But until we have that, you kind of got to use your own judgment in terms of these sorts of statements. Is that plausible? I'm not an expert in science education, wish that I were, but it's a similar thing in science education, isn't it? Do we not have in science education the best way for children to learn science in primary school is through doing experiments? I suspect in science education there may well be the papers written to support that hypothesis. That's good. Okay, they've been at this considerably longer than we have over in computer science. And, your own personal direct experience, think back to your primary school days. Do you remember the lessons of copying notes off the board or the teacher telling you things, or do you remember the lessons where you did the experiments? My guess is it's the experiments that stick in our mind. Ditto with the computer science. The best way, I'm sure, almost sure, is through this practical experience of coding. But it would be nice to actually start doing the experiments about that. So we've been doing this for a while now, not as long as the science team have, but Mindstorm's Pappett's book written back in 1980, he talked about how children who'd learned to program could use really concrete computer models. They were thinking in terms of computer code. They were thinking in terms of how the computer would work. Not just as an end in itself, not just to do the coding bits, but to think about thinking and learn about learning. And in doing so, enhance their powers as psychologists and epistemologists. That's what you want from your pupils, surely, to develop their powers as psychologists and epistemologists. Well, yes, actually that is going to serve them much better long run than being able to write some Python code. We teach them the programming so that they can think about thinking, learn about learning, become better psychologists, become better epistemologists. Not because we need more software engineers, not because we need more computer scientists. You don't teach your pupils poetry because we need more professional poets. You teach them poetry because it's a way of understanding the world and it's a medium for their creative expression. Ditto the coding stuff. It's a means to an end, not the end. Oh, so more from Pappett. So this was actually from P writing back in 1983, talking about actually coding on its own didn't seem to get to the end. You had to actually change the way you taught to emphasize what he called back then the planning skill, what we would now probably label as computational thinking. With accompanying instruction in thinking skills, developments in planning skills computational thinking may be achieved, but not just by giving children programming exercises to do. Okay, that's by way of introduction. I want to talk a little bit now. I want to show you some practical activities that you could do with real-life children to help develop some of these ideas. And I want to focus particularly on the algorithm bit of computational thinking rather than the logical reasoning. Okay, could you please, on the piece of paper in front of you, follow the instructions you're given, draw a circle for the body. Okay, there are people who are wanting to write on pads. That's fine, writing on a pad is fine. Add 2 eyes, add a crown, add some wings, and then add 4 legs. Don't look at your friends. OCR would be in horror about people looking at what their friends are doing, okay? To work independently. And have a look at what people draw. Oh, that's nice. Okay. Beautiful, well done. Okay. Very, very similar. Oh, I think we've got our eyes there. Very, very nice. Sorry, first of all, bring that back to okay. Very good.
is identical to that drawn by the person who sat next to me. Wonderful, that's lovely, isn't it? Nobody's got exactly the same frustration. But I gave you all exactly the same instructions. Not all good students, almost all good students. How come you don't want the same thing? Anybody? How come it's not exactly the same? Didn't I just tell you? Computers are deterministic machines, they always do things exactly the same way. This is a majority. Anybody like to answer why would I consider it? Yes. Yeah, and this is an issue, isn't it? In your algorithm, your sequence of steps might be good enough in your mind, but when it comes to programming, you have to use very formal language, you have to really pin things down. This is an example of one of the activities from Barefoot computing, which I mentioned earlier. Jane Waite wrote this. It's a lovely way to introduce this idea of having to be precise when we're writing a sequence of instructions, and that need for precision in the way you frame these sorts of things. I think Jane Waite's class was probably more creative, but look at these lovely answers to that, and that's a nice way into getting children thinking about these things. I want to talk now about food and drink, a subject close to my heart, indeed arteries. So let's start with the pizza question. I said earlier that an algorithm is a sequence of steps to get something done. Again on your own pad of paper, no more than 2 minutes. Yeah, no more than 2 minutes. Let's try and speed this up. Could you please write down your own recipe for pizza? Yes, write that down as a good answer. It's a really good answer. Getting somebody else to do it for Okay, so we have a gentleman who's destined for career in school leadership here. We see this as a delegation problem. You know, this is a very, very high level of abstraction, phone dominoes, okay? It works, it gets the job done, it really does. But we're managing that complexity. Think about all the abstraction that's involved there, yeah? We're not worrying about that level of complexity. Down the other end of this side of the room, so those of you sat in the middle, it's probably a deliberate choice. Okay, could you tell us I think that's pretty much what's going to happen in user express or even dominoes, isn't it? We're moving inside those abstraction boundaries and dealing with some of that complexity ourselves. So essentially your recipe is something about make the dough, make the tomato sauce, spread the tomato sauce on the
pizza, add the toppings, add the other bits. Notice pattern and generalization. Is there anybody in the room who wanted to ask me what sort of pizza? Because it does matter, but I guess it's Domino's probably have just the one recipe for almost all pizza, which will just add variables for whatever toppings you want on there. Yeah? It won't always be the same topping, but we can swap that in, swap that out. Nobody in the room, okay, we had at least 2 people were making the base, making the tomato sauce. Did anybody cross the abstraction boundary into how to grow tomatoes or how to grind flour? Okay, because at that level of detail we cease to care, and just like the gentleman here who said phone dominoes, we get somebody else to solve the problem, that problem, for us. Programming is like that. You don't need to worry about how the data is stored in the hard drive or on the silicon chips. Other people manage that for you. You don't need to worry about the machine code running on the central processor. Other people solve that problem for you. Other examples from the world of food and drink, making tea. And this is classic from 1980s flowcharting. I just wanted to draw your attention to British Standard 6008, which is the British standard for how to make tea. Okay? It includes there preparing with milk. Do you ever have that thing about, do you put the milk in first or do you put the milk in last? Hands up for put the milk in first. Hands up for put the milk in last. Okay, putting the milk in first is British Standard 6008 compliant. The rest of you, your tea doesn't meet the standards for the British Standard here, okay? They give reasons for that. Do you remember that bit in the teaching standards about not undermining fundamental British values? Covered that? Okay. My friend Phil Bagg does this lovely activity of getting children to write down the algorithm for the jam sandwich. He has the outtakes video. Let's have a look at that. Okay, can't get the YouTube to work. Never mind. But the sandwich bot video is brilliant. We do it with the trainees at Roehampton. I take on the role of the sandwich bot and have to follow the instructions I'm given, doing it exactly as the trainees in their recipe say. What do you do, though, when the trainee says spread jam on bottom? Move on to the next slide would be my answer. Okay, how are we doing for time? Think of a number games. You can do this a lot. Step out of the deck, stay on the deck. Let me just talk you through it, because then we can show more slides. But it's well worth doing as the exercise. Okay, I'm thinking of a number between 0 and 1,000, and we go around the class trying to work out what that is, asking yes and no questions. Over in maths, they ask really weird questions. They ask things like, is it a prime number? Or does it end in a 5? And it's really hard to keep track of all of those answers. Over in computing, we say, is it bigger than 500? Is it bigger than 750? Is it bigger than 875? And we divide and conquer each time. If you try it with a class of young enough children, their approach will be something like, is it 3? Is it 295? Is it 118? And just calling out random numbers. It will get there, but you've got to keep track of loads of information, and it's really slow. Try it with a slightly older class, and they'll have the idea of a systematic process is much, much better. So is it 1? Is it 2? Is it 3? Is it 4? We'll eventually get there. We're guaranteed to get there. And we only need to keep track of one previous bit of information. The rest of you can switch off until it's the person before you's turn, and you know what question to ask next. The divide and conquer approach, is it more than, is it less than, is it more than? You only need to keep track of 2 numbers, the highest and lowest possible limit, and you get there in 10 goes. It's incredibly efficient. We could have a go at this in Scratch, assuming this works properly. Oh, it's struggling to pick up the Wi-Fi. Let's go back into the deck and move on. Okay. It's also the algorithm you use for working with a dictionary. Do we teach children how to use a dictionary? I think we probably still have to. Although teaching, generally, if you want to look up what a word is or how it's spelled these days, you'll go to a search engine, probably begins with G, got a double O in the middle, I don't know. But using a dictionary, you don't look through from the beginning until you get to your word. You split it open halfway through, is it before or after this point? split that half open halfway through, is it before or after that point? And you get there so much quicker when looking at each word in turn until you get the word that you want. Is that something you need to teach children, or will they learn that for themselves? There's also, when it comes to finding things, we would come back to Google. And there in the computing curriculum, this is one of the algorithms we expect primary school children to know how Google search, selects, and ranks a set of results. Very briefly, if you type in computing CPD to Google, what does it do? It does not go off and search the web there and then. Despite their semi-miraculous powers, even Google cannot search the whole of the web in the 0.67 or 0.34 of a second that it takes them to return their results to you. It looks through its index of a copy of the web that it had made some time previously. Google have little clever programs that just go and ask for web pages, bring them back to Google's computers, store them in their vast data centers immeasurable to man, okay? They then look through the content of that page in building up an index as they go. So if the word computing comes up on your page, in the index for computing will be an entry to that web page. If the letter CPD come up on the page, in the index for CPD will be an entry for that page. You type in computing CPD, and what Google does is look through the index for computing, the index for CPD, and say it's the intersection, the Venn diagram overlappy bit, of both groups that you're actually interested in. And that's the list of, 600,000 search terms or search results it provides you with. Putting those into order is the clever thing. And top of the list, underneath the sponsored results, which are on pay-per-click, is the pages which have the most inbound links from other high-quality pages. So how come Wikipedia is so high? Because loads of other websites, including very high-quality websites, link to Wikipedia. How do you get your school website high up a list of Wikipedia results? Link to it from Wikipedia. Wikipedia does well. Your page would do well if linked to from there. There's the diagram explaining that. We are almost out of time. Let me just skip through to more interesting things down the bottom here. Okay, computational thinking across the curriculum. This isn't something you need to confine to just your computing lessons. If you're teaching Key Stage 1 or early years English, you're likely to have poems a little like this. Use your pattern recognition, use some sort of algorithm. What's the rule here to tell me what the next verse of the poem would be, or get children to predict what the next verse of the poem would be. Over in mathematics, we do talk about algorithms as the standard way for solving problems. When we introduced the idea at Roehampton, our trainees already know about algorithms because they've already been doing it. In maths, we have different ways of solving simple arithmetic. Just out of interest, 2 algorithms there for subtraction. Tell me, is there anybody in the room who uses this one, the one on the right, as the way they do subtraction or they teach subtraction? Okay, did you know that it's there in the national curriculum as one of the 2 approved algorithms for subtraction? Okay, it's there, it's on the list. Okay, over in science education, sequence of steps or set of rules. Set of rules is really, really useful when you're working at the Natural History Museum or London Zoo or Kew Gardens or one of these places, and somebody gives you the plant or the animal and says, "What's this, please?" We have a sequence of rules that we work through. It's a little like our divide and conquer. So if we're doing the mini beast safari, does it have any legs? Does it have 6 legs? If it's got 6 legs, what sort of animal is it? Okay, I'll leave that as an exercise for you. Okay, was anybody in school just before Christmas? Were you on placement then? Who was working in a school where they put on a school play for Christmas? Nativity play, something like that? That's not listed on the national curriculum. Doesn't say you should be doing that on the national curriculum. Glad that you were allowed to, though. Putting on a play, let's put on a show, is about algorithmic thinking. It's about taking a big problem and breaking it down into smaller parts. It's about abstraction. You manage the complexity. Don't make the costumes yourself. Get somebody else to make those costumes for you. Parents are good for this. Don't learn the lines yourself. The children should be learning the lines. That's a level of detail that we as the director-producer don't need to worry about. There's so much of this. Oh, and the analogy to characters wearing costumes following a script on a stage with Scratch programming is a really very, very nice one. Your line of work includes loads of abstraction and decomposition. Hands up who in the room thinks that the Secretary of State is interested in what you put in your lesson plan. Okay, somebody's hand about went up. No, just an itchy nose. Of course she's not. She's far too busy dealing with other things. That's a level of complexity which she has managed by getting other people to take an interest in that. Similarly, the gentleman here destined for career in senior leadership, you're not going to worry about the lesson plans for your colleagues, are you? You might want to see their medium-term plans or their schemes of work, but that level of detail you can deal with as an abstraction. My teachers can deal with that sort of thing. So we take big, complicated problems, delivering a curriculum, meeting a specification, and decompose them into smaller parts and deal with layers of abstraction in that process. There are so many opportunities for computing, just as there were for the old ICT across the curriculum. So some ideas for cross-curricular computing projects. The journey of a packet, one little bit of information going from my computer over to Google's servers. How does it get from my computer to their computer? And then plot that on a map. Have a look at how far it goes. Have a look at how quickly it gets there. 5,000 miles in 0.01 of a second. Anybody do the maths? About 3 times the speed of light. How does that work? Okay, document structure in HTML. Don't word process stories, write them in HTML. Making a clock, lovely old design and technology project. In Scratch, you can actually make a working clock that ticks itself, that adds 1 to the number of seconds every second. Other examples there, making a solar system. No, don't make a real solar system that requires special hardware. The resource budget is horrendous. Make a simulation of the solar system in Scratch. That's much, much easier to do. Scratch doesn't have any code for dealing with fractions. If you want to do my tables test thing there by adding fractions together, you've got to teach Scratch how to add fractions. Better still, decompose, deal with abstraction. Get your pupils to teach Scratch how to do fractions arithmetic. What better way to learn it than writing a program so that the computer can do that? There are other examples on the list there. How many schools are preparing children for the zombie apocalypse? That's something which we ought to have covered on the national curriculum. Really is. But you can simulate the zombie apocalypse using Scratch as a random model. There's my solar system. Sorry, simulation of the solar system. There's my clock. The links are all live on the slides there. If you want to find out more about this, pay attention to your brilliant lecturers at Leicester. Go to the other sessions later on today, but also have a look at the primary guidance thing, computing in the national curriculum. Quick Start Primary Handbook is fabulous, even if he does say so himself. Barefoot computing resources I've mentioned already today. And Join Computing at Schools. Who's a member of Computing at School? Okay, if you're not happy, guaranteed refund on your membership fee. How much is the membership fee? I think it's free, isn't it? Yes. Okay. Right, and that's me on the Twittery thing. There's an email address there. If you want to see the slides again, then I've got slightly the wrong thing compared to the hashtag bit.ly, LU, PGCE, ICT 2015. Most of the slides have live links to things I've been talking about. Thank you ever so much for your patience.